So in the last lecture, we discussed actually the vector model of an atom. Last lecture, we discussed vector model of atom. We found that J is equal to L plus S, and where cos Ls is equal to J plus minus L into L plus 1 S into S plus 1 divided by 2 under root of L into L plus 1 into S into S plus 1. And we also found that in external B, which is along Z direction, J presses about B, and L comma S both presses about J, related to J actually. So this is what we have already discussed in the last lecture. So up to now then we can say that the quantum state means quantized energy states of an atom. So it is quantized energy states of an atomic electron. That means quantized energy. Quantized means that when we denote the electron in a particular energy level by the quantum numbers, we used full quantum numbers to describe its position, then it becomes its quantum state. So for a particular value of N, L, ML, S and J, in the absence of any external field, this is in the absence of external field. So for a particular value of these numbers, we will get a quantum state of an atom, of electron. So therefore, any electron, when we have 0, 1, 2, 3, L, we have S, P, D, F, G, H electrons. So we denote them by this number of electrons. So this S is an orbit, it is not a spin quantum number, so please remember that. So you can similarly find different values of then particular value of S, then J, depending upon the electron, valence electron, because for even electrons, S is equal to 0. So for odd, it is half integral 1 by half h cat. For even, this is for even, this is for odd. And the total orbital quantum number is J equal to L plus S. We can write it as it is L plus half, and this is the spin orbit interaction which we discussed in a vector atom model. L minus half. Now what Stern-Gerlach experiment actually did? This was all we have previously seen these things. Actually, we have discussed this. So the Stern-Gerlach experiment actually was an experimental approach to find the existence of spin magnetic moment of an electron, of an atom. They, however, did the experiment, but they were not able to conclude that it is a spin magnetic moment. That was later on confirmed by Uhlenbeck and Goudsmit that it is a spin actually, but the experiment was done by Stern and Gerlach. So this became the basis for proving that there is a spin magnetic moment or a spin component of an electron of an atom. So the experiment all actually it was done in 1921, and it was not easy for them to do this because in 1921 they got the result actually, but they started this experiment in 1917. It almost took them 2 to 3 years to get some result, to take a final conclusion from the result. And sometimes they failed, sometimes they succeeded. They finally succeeded by verifying the theory in 1921, Stern and Gerlach. 1921. And this demonstrated directly that when an atom so it demonstrated that when an atom placed in the external magnetic field, that an atom when placed in an external magnetic field can take only certain discrete orientations with respect to the field. That means when we put a stream of atoms or an atom in external magnetic field, this atom can take, or the magnetic moment of this atom, I will not say the atom directly, but the magnetic moment of this atom, especially the orbital as well as the spin magnetic moments. So with respect to the field, it takes a certain discrete orientation, so it is not continuous. So there is some discrete orientation in the with respect to the field. And they say that Stern and Gerlach concluded that it is a space quantization. That means the quantization of the orbital angular momentum with respect to the applied field. But later on, it was not that. It was actually a spin angular momentum. And how it all happened, we will discuss it in this class. So this experiment, it also demonstrated the existence of electron spin, and hence it proved to be an verification for a vector atom model where we have taken both spin as well as orbital. So this gave the two purpose. So we got two purpose from doing this experiment. And if we see the plan of the experiment or the arrangement of the experiment, they took silver, heated at very high temperature, and it was vapors, silver vapor. So it was vaporized by temperature in an oven. So it was there were vapors, silver vapors in an oven. Why did they take the silver? Actually, there is a reason for that, and we will discuss that. So the oven was placed here, and since this is an oven, they heated it, and there were vapors. So there were vapors; they were out from this direction. and there is a slit here. Bisma has some problem here by joining. So there's a slit here. This slit will, what will it do? It will collimate the beam of those silver vapors, actually atoms, silver atoms here. So it will collimate and it will keep them in the one direction. They will not spread out. So the beam was used, slit was used there. There was another slit near the magnetic field. This magnetic field was a non-homogeneous. It was not a homogeneous magnetic field. And there were pole pieces specially designed north to south. So there were it was a non-homogeneous. Non-homogeneous means the south pole has more strength than the north pole, or the north pole has more strength than the south pole. It was just to exert the force on a particular direction so that we can distinguish between the two. There is a separation, there is a well-defined separation in particular direction. And what they found on the screen, there is a screen here. This was a magnet. These are the slits here. This is a screen. And when they here decide like this, there's no component in the center. Remember that. That is one of the important point here in this experiment. And the convention is like this. This is the x direction. This is the z direction here. So the field is in the z direction. There's a B here in this direction. And the displacement, let me denote that S, that is in the x direction. Displacement of the beam from one point to another point, that is in the x direction. This is all the schematic. It's not the exact setup. It is a schematic. How the setup was performed, how the setup was designed actually by those. So I hope you have understood it. How, what purpose did they do? So the one aim of the non-homogeneous magnetic field was that the field gradient changes actually when you move from this point to this point. The gradient changes, that is delta B by delta Z. Del Z, it changes actually along Z direction. And when it changes, the separation or the orientation of the magnetic moment will accordingly change. And we will see that it is directly proportional to that. So whenever the beam leaves this magnetic field here, it is received on this photographic plate. This is a photographic. I already told you silver, when it falls on a photographic plate, it actually gives us transitions which can be decomposes that screen actually. That screen is of some halides and we got some images on that. And it is important to note that there were no traces of the direct beam on photographic plate. And only two traces were found. Only two traces, that means two structures, two characters were found on the screen. Just a minute. And these were symmetrically placed on the screen. That means I will draw the cross section. If this is a screen, they were like this with respect to this center axis. This is what they found on the screen. Actually, beam. This is the traces of those silver beams here. Atoms. Plus and minus z direction. Plus and minus components. So if we take this as an origin, this here, what they found in the screen was one component here, another here. That is how I draw here. This is X, this is Z. So these were the results. This was the setup and how they interpreted the result. So we know that whenever we keep a beam of charged particles in a magnetic field, there's a force, deflecting force, which depends on the orientation of the magnetic field actually. And we know that these silver atoms behave as tiny magnets. Hence they have dipole moments. Hence they have dipole moment. In this, and they interact this dipole moment. It interacts with external B. So the magnetic field will interact with the external magnetic field. This magnetic moment is a magnetic field will interact with the magnetic moment of those silver atoms. And the important point about the silver atoms is that silver has an atomic number of 47. Out of these 47 electrons, 46 form closed shell configuration. And what we are left with? We are left with one electron which is in the s orbital. One electron, 47th electron, which is in the s orbital. So it implies L is equal to 0. We don't have any contribution to the magnetic moment from the orbital part. So there is no contribution from the orbital angular momentum to this. So whatever the magnetic moment comes, we know that J is equal to L plus minus S. That is only because of this S. Okay, that is how this theory was actually these two components. This corresponds to 1 by half, this corresponds to minus 1 by half, but Stern and Gerlach did not prove this. They were not able to locate this exactly. If anybody wants to talk, he can write a message here. So if we don't have any quantum mechanics, if you take a classical mechanics, under classical mechanics, in classical mechanics, there is no quantization. No quantization actually. And when there is no quantization, the image which you will be able to find on the screen will be a continuous one. It should be a continuous one according to classical mechanics. But this was not the case, which has been observed in the experiment. They instead obtained only two air which were equally spaced. And if you take its cross section, whatever I have shown earlier, This was symmetric with respect to the central direct beam. So this showed that atoms passing through the field were oriented in space in discrete directions, and this gave us the discrete states on that photographic plate. So the beam deflected in certain directions and gave the discrete traces of that beam. We got the discrete trace of the beam on that plate, and this gave actually the space quantization proof in the case of silver atom and in the presence of external magnetic field. So if you see mathematically, if we go mathematically, what we obtained in this, the magnetic field, external magnetic field, exerts an average transverse force experienced by the atomic magnetic. So one point is important, that if it had been a uniform magnetic field, we will have that such type of that Lorentz type of force actually. But to avoid,
repeat.
So the external magnetic field here, this exerts an average transverse force which is experienced by an atomic magnet. Atomic magnet means silver atom. So you have north and south. This is an inhomogeneous magnetic field. So if this is an inhomogeneous, if it was homogeneous, one thing was that Lorentz force and the contribution from intrinsic magnetic moment will be suppressed. That will be suppressed there. So they took it inhomogeneous just to differentiate and to see the contribution from the internal magnetic moments, intrinsic magnetic moments. So we know that whenever we place a magnet, or that is a magnetic dipole actually, that atomic magnet is, those are the magnetic dipoles, they are placed in this external magnetic field. They store potential energy, U. Placing a magnetic dipole in an external magnetic field, and energy is stored in that system, in the dipole, and that energy is equal to mu L cross B. Okay, and it is, I think, minus mu L dot B, not cross, mu L B cos theta. So it is it mu dot B or mu cross B?
Dot.
Use dot. Yes, it is mu minus mu L dot B.
Yeah.
Okay, and we know that the this is a vector. This is a vector. This has it is mu L. It is I component in the x plus j component in the y j component in the y and k component in the z direction. So it is y plus k mu L in the z. Sorry, either you place it or here or here.
Q dot B है सीधे माइनस नहीं
Mu it is mu L dot b minus.
माइनस नहीं है शायद सर
The minus is that because that mu L has an opposite direction because it's a negatively charged particle. This is B,
ओके सर
this is mu L here. Okay, so that is how it is minus actually there. So mu L this and this is actually minus here, and B is again equal to BZ only. We have direction only BZ. When you take the dot product of this, you will get U equal to minus mu LZ BZ, because they have the opposite directions, and that is pi. We also know that the force F which is exerted on those silver atoms is equal to minus del U gradient, and this gradient is along the z direction because the field has a direction along the z direction. Okay, then it gives us that this force which is exerted on the atoms of the silver in the z direction, that is plus del B by del Z, and this B is in the Z direction, and it is total at this mu J. I will write Z because J will be L plus S, L plus minus S, because whatever the atomic magnetic moment will be total magnetic moment of that atom, that is L plus minus S, depending upon the orientation of the S. So this is the rate of change of field, because we have a non-uniform magnetic field, so it will change. It has a gradient along the direction, and I can write it as mu J. This can be written as it is minus Gj E by 2m into J. It is equal to minus Gj. I can write mu B 2 pi by h cut. Sorry, h, not h cut. Sorry, it is h into J. And we know that this expression we have already seen from mu L, mu S, and mu J in the last lecture. G is the corresponding G factor. Mu B is the Bohr magneton, which is EH by 4 pi m actually. EH by 4 pi m. So mu B is equal to EH by 4 pi m. This is Bohr magneton. Now we are applying the magnetic field which is along the Z direction. So mu J is, and mu J will be the quantized Z. Like we have LZ, we have a mu JZ, the Z component of the magnetic moment, total magnetic moment, which will precess around this, which will be along the direction of the magnetic field, is minus Gj mu B Jz, total angular momentum along the Z direction. I can write it as minus Gj mu B is 2 pi by h mj h cut, this jz is equal to mj h cut, and which is equal to minus gj mu b m. Now using this value in that expression fz will be equal to delta bz by del z, it is gj mu b mj. And remember that this mj has values of total possible values 2j plus 1, like we have 12 plus 1, and it ranges from plus j through 0 to minus j. Now since we are having a force which is acting on a charged particle, so the charged particle, okay, we will discuss it at end. The question is there, I will discuss it at end, no problem. Now the force is acting this fz along the z direction on this particular charged particle. So the charged particle will be accelerated, and the acceleration will be fz by m, where m is the mass of the atom. Okay, this is simply F is equal to m into a, which is 1 by m. Using this expression, it is delta bz by del z gj mu b, this acceleration, okay, of that particle, of the atom, silver atom actually. Now silver atom is moving along a x direction, but it can be deviated towards the z direction. So Vx is its longitudinal velocity. Let Vx is the longitudinal velocity of silver atoms, and d, if the length traveled along the x-axis, length of their path, which is traveled by those silver atoms along the x-axis in the magnetic field, then during the time t, in time t, during which the atoms will experience the transverse force because of the applied external magnetic field. So t is a time during which the atoms will experience the transverse force, and that t can be written as, it is d upon Vx. No, this is d upon Vx, where d is the distance which is traveled along that. This is a path, length of the path. Vx is the velocity, longitudinal velocity of the atom, and t is a time during which it moves under the influence of the magnetic field. That means the transverse force exerts on this. Now you know that if we have an particle having velocity Vx and mass m, and it is moving with some energy, it will have a kinetic energy. That kinetic energy will be equal to Vx square. We will use the kinetic theory of the gases because we are treating the gases at high temperature. This is a vapor phase of the silver, and we can write it as 1 by 2 kT, equipartition of energies. But remember that there will be 4 degrees of freedom. The degrees of freedom actually increases because As T increases, temperature increases, the more and more degrees of freedom increases. At low temperature, we can have translational motion actually. Translational motion. As you increase further, there will be a vibrational motion, and when you increase, this will be at higher temperatures. Before this, there will be a rotational motion. So these will decide the different degrees of freedom which will be available to a silver atom which is at very high temperature, such that it is in the form of vapors. So we will have 4 degrees of freedom in this, and from this we will get that what we will obtain 1 by half of m Vx square is equal to 2 kT. And it has higher probability, that atom, silver atom, to falling on the hole through which it is emitted because of that very high temperature. So if we calculate Vx from this equation, divided by m. Also, T will be equal to then here, using Vx here. So T will be equal to d upon Vx, which will be equal to d under root of m over 4 kT. So the transverse deflection, total deflection, you know that if we have a particle which is moving from this point to some another point, having initial velocity u, having final velocity some v, and it has an acceleration a during time t, then the deflection total, or the distance traveled under the transverse force, let us suppose that is z, that z is equal to ut plus 1/2 of at square. Okay, so when it starts from here deflecting, we'll assume that it is at rest here. Okay, so this is the point where it starts deflecting. So when it starts deflecting here, we assume from that it is being at rest at this point and take its u equal to 0. So z will be equal to 1 by 2, it is acceleration in the z direction, at square. If you put up the values of a and t from the above, a we have already, this is the t, we have also calculated a here, this, using these values in this expression, because z will be equal to the total deflection which it suffers d square is not d2 square, the differential, it's not a double derivative, remember that. It is simply a square of this distance path. So I can write it as it is gj mj this is the total deflection which is under the influence of external magnetic field, that is a transverse force that is directly proportional to the gradient along the direction. This Bohr magnet, and actually there's a constant and this path. Other things are here and temperature, others are all constants. So if you see this expression, there's an mj, and mj suggested that we have 2j plus 1 components corresponding to the possible values of mj, and 2j plus 1 traces on photographic plate. So for silver, there were two traces, which I already told you that there was L equal to 0, S was there only, so S may have two possible orientations. That is why from those two traces actually came. So, and we can write then that Gj Mj is plus minus 1. One is in the above direction by measuring the separation between the traces. So that Gj Mj, because they were not knowing that is a spin component, so they put up it as plus 1 and minus 1 simply. And it was assumed that the silver atoms at this such high temperature, they are in their ground state, so no excited state. Silver atom, that means we are treating silver atoms at ground state, and for that L is 0, J is S, which is 1 by 2, so 2J plus 1 will be 2. There are two components. There were two traces. And also the orbital G factor for J and for spin, it is equal. This is 2. So Mj is Ms because Ml is 0. Remember that. We have Ml 0. So therefore, if you write Gj Mj, it is 2 into plus minus 1 by 2, that is plus minus 1. That's what they have observed actually in the experiment. This is how they gave a quantitative treatment, mathematical treatment of this. And like this silver, we have the ground state of like zinc, cadmium, mercury. They all have L equal to 0 and J equal to S state. Sorry, it is not for these atoms, it is L is 0, S is also equal to 0, not half. They are completely filled. And J is also 0. And this gives us Gj Mj equal to 0. That means that beam will not be deflected in this field. And they have observed actually in this experiment. And about the spin, that there was existence of electron spin. This was shown actually by experiment by Phillips and Taylor in 1927. And they repeated this experiment of Stern-Gerlach using a beam of hydrogen atoms. Taylor repeated Stern and Gerlach experiment for hydrogen atom. There's only one electron, and they again found that there were the two traces. J was L plus minus S, and 2J plus 1 is equal to 2. Now remember, now see here what the need of inhomogeneous magnetic field. What is the need of? Suppose that this is a magnetic field, this is a dipole which you have already studied. Then it exerts a force. This is a uniform magnetic field. That means a homogeneous magnetic field. When you have an homogeneous magnetic field, what will happen? The magnetic moment, magnetic dipole, that is an atom, it will experience actually a turning moment. Turning moment means torque.
Talk.
Yes. So it will actually experience a torque, but not a deflecting force. It will not be a deflected, it will be turned. And in this case, we will not be able to obtain the deflected components of that incoming beam, irrespective of the orientation of them with respect to external magnetic field. So what I am saying is, I will repeat it, that if we have had an uniform magnetic field, in the uniform magnetic field, our beam of atoms will actually obtain a torque. They will experience a torque, not a deflection. Deflection is something different than the torque. Torque is a turning. So we will not be able to obtain them separately on that plate. Okay, that is why they took actually a non-homogeneous magnetic field. Another point is that why they took atoms, not ions. The reason is simple. When you have atoms, a neutral atom, when it is passed through an inhomogeneous magnetic field, then each atom experiences a transverse force. Now, if we have charged ions, what will happen? Charged ions will experience a Lorentz component. And we will not be again able, they will be moved like this. They are coming and going just like this. If they are coming, they can just go like this. It depends upon their charge. So, and we will not be able to again find a trace on that photographic plate. Okay. If anybody has any confusion or concept in their mind, please discuss.